During the 19th century, scientists were using spectroscopy to study light emitted by various gas discharge tubes. I believe in your chemistry class you viewed a gas such as helium or hydrogen or neon through a spectroscope. I can also show you that in class. Light from a typical incandescent light bulb produces a continuous spectrum when we view white light through this diffraction grating. You've seen this before. I've shown you in class a demonstration with my overhead projector and a diffraction grating when we were studying the interference and diffraction of light. Now, if you replace this incandescent light bulb with a gas discharge tube or a heated lamp of heated gas or neon or whatever it is, you'll end up with the emission spectra that is shown over here, sometimes called the line spectra. Each of these lines represent a wavelength of light. And you might be thinking, but how do these discharge tubes work, or this lamp with the heated gas? So let me just take a little brief side trip over here on the side to talk about what happens here. So imagine I have an evacuated tube which I fill in with some gas, like a hydrogen gas. And on each end we have electrodes, which then I attach to a high power supply, high voltage here. So I have a high voltage across here. And in this tube I have a bunch of protons, electrons, which represent the gas. And when this is hooked up to a high power supply, I suddenly inject electrons into this gas. And these electrons are essentially accelerated from the high voltage that is caused between these two electrodes, and they bump into these gas atoms. And as long as there's a high voltage and a current that is established, then you'll get this gas emitting light. And these light waves are really like photons. In the addition of studying light emitted by a gas, scientists also studied the absorption of light. So if we took a white light, say from an incandescent light bulb, and this light were to shine through one of these tubes, these gas discharge tubes, then as this light waves come in through here, this white light that goes through this discharge tube, we find that we only get certain frequencies that come through. We're basically missing wavelengths of light. You basically get something like this resulting absorption spectra that shows these dark lines here, which are these missing wavelengths that were taken away when the white light went through this gas discharge tube. So when the white light, or the heated gas, passes through a diffraction grating, you end up with this, which is basically the line spectra, or you can call it the emission spectra. And then if you send white light through a discharge tube, you end up on the other side here with these missing lines, and this is called the absorption spectrum. Scientists soon began to realize that each element, like hydrogen, helium, neon, had its own characteristic line spectra. For hydrogen, the formula that predicts the spectral lines was found by a Swiss mathematician named J.J. Balmer. The formula looked like something like this. So the wavelength could be determined for each of these separate line spectra, and R was a constant known as the Rydberg constant. You don't have to know how to use this formula for the AP exam. What is important to realize from all of this line emission and spectrum is basically that the experimental observation of these emission and absorption spectra of gases of these discrete wavelengths was impossible to explain with the early models of the atom. Which brings me to the Rutherford experiment. But I'll leave that for another lesson in the next video.